Okay, so so far we have investigated mostly the design of integrated circuit. So circuit made of transistors, basically. At the end of the module, we have reviewed how to build an operational amplifier. Operational amplifier are basically the key ingredient to implement multiple different analog subsystems. So this second part of the course will be dedicated to how to combine op-amps into realizing more complex functions, and in particular filtering functions, which are truly pervasive in every system integration task. Here you can find some books which are quite useful for the system engineer. In particular, I would recommend this book by Rovitz and Hill, which is The Art of Electronics, which is indeed very practical in its age. Okay, so let's review the basic task which should be made with analog circuit design. So why indeed the signal conditioning is needed? Well, first of all, as we said in the introductory statements, analog circuit design is mandatory because the world is analog. So whenever we have to interface the sensor to a digital system, we need some analog interfaces. The idea is that an analog interface indeed is consisting in multiple sub-functionalities. For example, the reduction of source loading, which means somehow adapting the characteristic of the amplifying stage and the filtering stage to the characteristic of the source. Then we have to provide some sort of gain in order to match, and in this sense to exploit as much as possible the dynamic range that we have at the input of the analog to digital converter. Before that, we may need some kind of filtering for basically two reasons. First of all, to avoid aliasing when performing the sampling. And then also, when we know that the signal is confined in a specific spectral region, we may exploit filtering to maximize the signal-to-noise ratio. Because typically noise, as we have seen, is white, okay? Apart from flicker noise, thermal noise, which is typically the most relevant component, is white, okay? Is flat in the power spectrum density. So to maximize the signal-to-noise ratio, we can apply some bandpass filtering centered around the spectral content of the signal. Moreover, we can use analog signal conditioning also to add extra functionalities to our sensor. For example, if we want to compute the integral of a given physical quantity or the derivative, we can do it numerically on digital signal processor, but it is by far more efficient if we do the same functionality in analog, okay? With analog circuit, we can do some mixing, okay? For example, in the audio signal word. Okay, so if you want to mix the signal information coming from the lead voice and the guitarist, you can do it with analog circuit rather than digitalizing all the signals and then perform some kind of digital mixing. So there are plenty of applications in which this kind of functionalities are needed. So starting from source loading, the idea of source loading is something that we have already considered when we have discussed the performance of the integrated circuit, in the sense that whenever we have a given source, like for example a voltage source like this, we have indeed also some parasitics due to the source itself. So the source will be characterized by a given source impedance. Okay. Then if we want to measure this quantity, what we can do is to apply a voltmeter here. Okay, but the measuring of the voltage, it is again inherently affected by some parasitics, so some kind of input impedance. Okay, so what we are actually measuring is not the voltage UG, but is the partitioning of this voltage between the impedance of the source and the input impedance of the readout circuit. So basically, what we are measuring is the voltage generated time the input impedance divided by the input impedance plus the source impedance. Okay, so in order to maximize the signal, what we have to do is to select a circuit so that its input impedance is as big as possible, as large as possible. Okay, so so that in this ratio the impedance of the source can be neglected. Okay, this is a possible situation in which we may need a very large input impedance, but we may have also a different situation in which it is the impedance value which is used to sense a given physical quantity. So the physical quantity is measured by analyzing the variations of the sensor impedance. Okay, there are many sensors whose working principle is this one. For example, strain gauges. Okay, what you are interested in is the variation of the impedance associated to the sensor. How can you measure such variation? Well, one way to proceed is to feed the sensor impedance with a constant current and measure the voltage across the impedance. Okay, so that the impedance can be estimated from the measured voltage divided by the current. Let's say I'm using this hat as to mean estimation. Okay, this is not the actual value, because when we measure the voltage, we have also some sort of input impedance in part. Okay, we cannot build the perfect readout circuit in which we just measure the voltage without having also some sort of input impedance. And again, it is mandatory to have Zi as large as possible, because otherwise the excited current will flow partially into the input impedance rather than flowing just in the sensor impedance. Okay? So source loading means that depending on the task that you have at hand, you have to proper force the input impedance of your circuit to be high for this kind of task, or very, very low for the task highlighted below. So in this case, the source is a current generator. We wanted to measure this current with this readout circuit, okay? And in this case, we don't want that the current generated here flows back in the parasitic impedance of the sensor. We want the current to flow as much as possible in this direction. And to do so, the input impedance of the current measurement system, we are measuring ampere, of course, should be as small as possible, okay? So that the current will privilege this path, okay? So in this case, Zi should be small, and also in this case should be small as well. So here, basically, we are measuring the impedance of the sensor with a voltmeter. This means that we are measuring basically the voltage here, with an amperometer. So basically the idea is that we are generating a constant voltage, and we are measuring the current which is induced by this constant voltage. The problem is that this constant voltage is partially applied to the sensor impedance and partially to the input impedance of the current measuring system. So again, in this case, it is important that the input impedance is as small as possible, because when this indeed is small, then also the voltage drop across here is small as well. Okay, so there are many different situations in which a proper design of the input impedance is important. And this source loading task is realized with the analog circuit. Second important task is related to the matching of the dynamic range. So suppose that you have a sensor which generates an output which is confined in this voltage interval. Okay, so this is the maximum output in terms of voltage that this generic sensor can realize. Suppose that we feed directly the output of the sensor to an ADC converter. The ADC converter input range accepts inputs up to this point. Okay? So this means that if we have this sensor directly connected to this A to D converter, even if this A to D converter may have a quite large bit depth, we are just measuring the least significant bit variations. Okay, so the idea is that the actual resolution of the system will be limited to few bits. So you see that there is a poor correlation between the resulting digital signal and the analog one. We are losing a lot of details. Okay, so we have to match the dynamic range of the source with the dynamic range of the A to D converter. Okay, how can we do that? Well, we had an amplifying stage. So in the new design, we had this gain stage. Therefore, now the sensor output after this gain stage matches perfectly the limit of the input range for the A to D converter. Okay, so the A to D converter input-output characteristic may be modeled like this stair function. Okay, so we convert this input here, for example, to this value. Okay, etc. And now what you can see is that the digital output, it is a much more, let's say, faithful duplicate of the input with minor quantization errors with respect to the original signal, which is this one in this light gray color. Okay? So now we are exploiting the full bit depth that we have in our signal. All 4 bits are reached by the output. Okay, so matching the dynamic range is another reason why we may need analog processing between the sensor and the A to D conversion. Well, maximizing signal-to-noise ratio, it is quite obvious concept. This is related to the fact that basically the area of the power spectral density of the signal is what we are interested in. So the good portion of the collected signal, while we have a large amount of power spectral density, which is totally useless and due to noise. So it is pointless to feed all this, the whole bandwidth here to the A to D converter, because this means that we are just passing noise to the A to D converter. So what we can do is to add a low pass filter, set the cutoff frequency in the proper region, depending on the maximum oscillation of the signal in terms of power spectral density, and then use the low pass filtering for the maximization of the signal to noise ratio, for enhancing the signal to noise ratio. Adding functionality to the sensor, what does it mean? Well, I've already given a couple of examples, so derivations, integration, or multiplication of analog signals, or mixing. These are all functionalities that can be efficiently realized with analog signals. So what we are going to see in this last module are some examples of these functionalities, how can be realized with op-amps and combination of this circuit, and how filters can be implemented. To analyze properly the analog functionalities for analog systems, like for integrated circuit, we have also to analyze the non-idealities associated to these subsystems. Okay, of course, we went through the analysis of operational amplifiers made by the integrated circuit, and we have learned that ideally we would like to have an infinite gain in the op-amp, but this gain, indeed, it is finite. And also we know that we have a lot of additional non-idealities, for example, finite output resistances and so on. Why do we want very high gain typically in operational amplifier? And another thing that we want is that indeed the differential gain is very high and the common mode gain is practically linear. Well, basically we want this because the operational amplifier are always connected in feedback loops, okay? And in a feedback loop, we do have a sort of, a feedback relationship, which is here is referred to as function h. And if we compute the input-output relationship, well, we will get back to this formula later, but let me anticipate this. Well, basically what we have is that V out over V in is given by G, where G is the gain of this, the differential gain of this op-amp, divided by 1 plus GH, okay? And if G is sufficiently large, GH is much larger than the unity, and therefore the gain can be approximated as 1 over H, okay? So the idea is that this network here is made of passive components, okay, typically resistors, okay, or resistor and capacitors, okay. Being made of resistors, so you can properly trim the value of the resistor to achieve precise gain with the implemented circuit. And so with the passive circuit means that H is typically less than 1, so it is an attenuating function. But when you plug a function which is less than 1 in the denominator, clearly you are still achieving the gain. Okay, so you control the gain with this passive function, and you use an op-amp just to set, thanks to the stability induced by the feedback, to the precision induced by the feedback, a very indeed precise gain. Okay, so in some cases, this guy is a voltage amplifier. The CMOS op-amp that we have seen so far, so the two-stage amplifier, the folded cascode amplifier, actually are more precisely referred to as operational transconductance amplifier, because what they do is to translate the differential voltage into a current. Okay, so they are characterized by a very high output resistance. Okay, you can also turn a transconductance amplifier into a voltage buffer, into a voltage amplifier, sorry, by adding an additional stage with respect to the ones that we have seen at the very end of the circuit. So the last stage could be, for example, a common drain amplifier, so that you had this extra stage, which is characterized by a very low output resistance, which is what is needed for voltage amplifier. And this last stage may be characterized by a relatively low gain, maybe a unitary gain, but the bulk of the gain is realized by the other function, by the transconductance amplifiers. Okay, so if you plug, for example, a folded cascode or a two-stage amplifier with a circuit with an additional common drain stage, then you get the desired voltage gain. Okay. Let's speak about non-idealities. Okay, so first of all, in an ideal op-amp, the output range should be very large, okay, possibly close to the global voltage swing, which is available in our circuit. So let's say from 0 to VDD. Okay, so this is what we would like to have, but in practice, we know that the output range of our circuit is limited, okay, because we want the device to work in saturation, okay? So first non-ideality is related to the headroom, which is wasted with respect to the values of VDD and the bottom value, minus VDD or the null value. Then another important non-ideality is the fact that we would like to have an output rigorously equal to 0 when the differential voltage is equal to 0. But this is not the case in all the practical realization of our circuit. So there is always a slight discrepancy between the ideal case and the actual case, and the actual value of the input in which we have the 0 value output is called the offset voltage. Okay, we have already estimated the offset voltage for a CMOS differential pair, if you remember, so that you may know that by playing with the overdrive of the elements of the differential pair, we can try to minimize the global offset value, but there are some quantities which are dependent on the technology. So again, even in the most sophisticated integrated circuit, this offset will never be rigorously 0. Okay, so offset is an important degradation of our circuit. Input range, here it is stated, well, actually, ideally 0 means that the gain is so, the slope is so steep that we have very fast transition between input, between the negative saturation and the positive saturation. So this is the differential input, okay? It is not the common mode input range, okay? This is another thing. This is the differential input. The differential input namely should be around 0, okay? So the device, the op-amp, should be biased in a condition in which there is a virtual short circuit between the positive terminal and the negative one. But this is not the case, again, because the gain is not equal to infinity, but it is finite. Okay, some other non-idealities. Well, in our estimation of the transfer function in op-amp circuit, we always assume that the gain is arbitrarily high, no matter what the frequency is, okay, of the signal. But this is not the case. We know that each op-amp will have a characteristic frequency response, and this response will be characterized by a trend like this, in which we have a dominant pole, then we lose 20 dB per decade or 6 dB per octave, and therefore, very quickly, we will have a gain which it is almost unitary. or even less than that. Okay, so the open loop gain is not infinite, the bandwidth is not infinite, the gain bandwidth product, that is the product of this guy and this one, is not infinite as well. Phase margin, well, ideally we want a very high phase margin, possibly around 90 degrees, okay, to avoid any overshoot effect in the frequency response when in the step response. But again, this is not the case. Equivalent input noise, well, this should be 0 for ideal circuit, okay, but there is no such a thing as an ideal circuit. Okay, so that our input noise, as you have seen also in the specification for the first project, it will be different from 0. And actually, the larger will be the input, the equivalent input noise, probably less power consuming will be your circuit. Okay. Finally, common mode rejection ratio, that is the ratio between the differential gain and the common mode gain. This should be also very large, but depending on the op-amp quality, this could not be the case. Other possible non-idealities are related to settling times or slew rates effect. Okay, so the settling time is more or less related to the inverse of the gain bandwidth. Okay, while the slew rate, as you may remember, is a totally different quantity. So if this guy here can be somehow computed, estimated by looking at a small signal circuit, while slew rate effects are totally different cases are related to the maximum current that you can drive to the load. Okay. So slew rate effect is the maximum derivative of the output with respect to the input. So ideally, we would like an output which follows rigorously the input, or it is just conditioned by the frequency, the dominant pole. While when the slew rate comes to play, you see you have this sort of triangular trend in the slew rate, which means that the slew rate induced also non-linearities in our signal. Okay, so distortion. Okay, I guess that you are familiar with this configuration here. This is the celebrated inverting amplifier. So in the inverting amplifier combination, we have the op-amp that is connected with this feedback loop consisting in R1 and R2. So the idea is that if indeed the op-amp is ideal, we have, as I said, a virtual short circuit here, because the differential input range should be equal to 0. If you have a virtual circuit, short circuit here, then this node is virtually grounded. This means that you can estimate the current which flows through R1 as V input divided by R1. This current flows in R2. Okay, because there is no alternative path, because in an ideal op-amp is characterized by an infinite input impedance. So the bottom line is that V out can be estimated as minus R2 time the current which flows through R2, which is VI over R1. Therefore, V out over VI is minus R2 over R1. Okay, so you can control the gain of your circuit just by controlling this feedback loop. Well, the problem with this configuration is in the fact that the gain here is not equal to infinity, and therefore you have not a perfect virtual short circuit here, but it is finite and, let's say, equal to capital A. So when you have this condition, this means that the output voltage shall be given by the value that we have here, which should be minus V out over A, because V out, if V out is V out, and V out is resulting from the multiplication of the differential input, since this negative input should be equal to minus V out over A. So this is it. So the current I1 which flows through R1 shall be given by the difference between VI and minus V out over A divided by R1. And this current here, again, must flow in this branch because we are still assuming that we have no input in the input impedance is infinite. Okay, so we are just considering a finite gain effect and not all the other non-idealities. So V out is minus V out over A time I1, the current which flows here, time R2. You can then replace I1 with the estimation of the current flowing in R1, so VI minus VA over A over R1, and time R2. Okay, so if you then collect all the V out terms in this equation and all the VI terms, what you get is this expression here. So you see the numerator is the original expression that we found when we have assumed an infinite gain. You see that the actual denominator is 1 plus a degradation which is induced by the finite gain. Okay, because this denominator here is larger than the unity. Okay, because it's 1 plus this term. Okay, this means that the actual gain G is less than this. Okay. This configuration here has many useful applications and also some very important extensions. So, for example, well, okay, so again, Plato and Aristotle. Okay, so here we have Plato with its ideality. And here we have the finite gain effects. So the truth, the reality must include also the non-idealities. Okay, an extension of the inverting configuration is the so-called weighted summer. That is a device which has multiple inputs, each one facing different resistors. Okay, so if you assume again the virtual short circuit, thanks to the assumption of infinite gain, then you have this node to 0, and you can estimate the current I as the combination of V1 over R1 plus V2 over R2 plus for each source Vn over Rn. Okay, so this current here then flows through Rf. So basically the current it is multiplied by Rf with the negative sign to compute the final value for the output. Okay, so the bottom line is that the output is given by the summation of V1, V2 up to Vn with different weights controlled by R1, R2, and Rn. Okay, so you can weight differently the role of the different sources. So you can use basically this circuit for mixing purposes. So this is an example of a 25 watt 4-channel mixer and amplifier. So the idea is that you have indeed the weighted summer at the beginning of the processing chain, and you can use potentiometers to change the weight of the different branches. Okay, you increase the resistance, you are decreasing the weight of the input. All these inputs concur to determine the current at this point. Current at this point must flow in this branch, thus determining the output voltage at this point. Okay, and you may have also a master volume which controls, again with a potentiometer, the global gain of the circuit. And then you may add an additional power amplifier to control the speaker output. Okay, so far you are in the signal realm, so low values. Here you are in the power realm, power electronics. Okay, so actually this circuit is realized with a common emitter. Okay, with some degeneration of the emitter and some capacitances to couple in AC this circuit with the power one. And then you have an output stage which is basically configured as a sort of push-pull configuration with a Darlington combination here, a C-like pair here. This device is just meant to have a unitary voltage gain, but with a very low output resistance and with the capability to drive very large currents, okay, to the output. Okay, so this is an example of mixer and amplifier circuit which can be applied for audio applications. Okay. Do you have questions? Okay, if not, let's make a short break and then we will see another possible combination of the inverting configuration. Okay, so the mixing behavior that we have seen in the previous circuit can be as just one fundamental limit, which is related to the fact that this is indeed an inverting configuration. Okay, so this is indeed an inverting configuration, which in some cases it is undesirable. So to achieve a non-inverting combination or to achieve the capability of adding and subtracting signal contributions, what we can do is to simply chain multiple inverting stages. So, for example, the output will be the inversion of input V3 and V4, but it will have the same sign of V1 and V2 thanks to the double negation, okay, inversion, okay. So the output here will be RA minus RA over R1 V1 minus RA over R2 V2, and then this output here will be multiplied by minus RC over RB to get to V out. Okay, so this is a sort of linear combination of all the phenomena that we have seen so far. So summing and subtracting can be implemented in this way. There is, of course, also the possibility of using the so-called non-inverting configuration, which is achieved by connecting the input directly to the positive input terminal of the op-amp and realizing the feedback loop through R2 and R1. In this case, as you may remember, the V out over VI relationship is given by this formula, which is assuming, again, a virtual short circuit between these two nodes, so that VI is also the value at this point. Therefore, the current flowing through R1 is in this direction is VI divided by R1. The same current must flow also in this branch, and thus determining a voltage drop across R2. And the final result is that we have this relationship, okay? You can easily prove it by just adding up to VI the voltage drop across R2, okay, and you get V out. The problem is that this non-inverting configuration result is based on the assumption that the gain is equal to infinity, okay, but there are some finite open loop gain effect also for this configuration. So if we replace the infinite gain with A, then we have this formula here. So you see there is a sort of degradation of the ideal transfer function by the effect of the finite value A. So let's try to see the origin, analyze the origin of this formula. So basically, let me sketch again the non-inverting configuration. So we have here R1, then we have the op-amp, then we have the input here, we have the feedback loop through R2, which is connected in this way. This is V out, and here we have a finite gain. Okay, so the output, well, if we call the voltage here V minus, okay, the voltage at the negative input, or let's say, yeah, V minus. So we have that V out will be equal to A time Vi minus V minus. V minus here is also the partitioning of V out over R2 and R1. So the voltage divider effect through R2 and R1. So this means that V minus can be written as V out time R1 over R1 plus R2. Okay, so the idea is that we are analyzing this circuit. V out, R2, R1, and V minus. Okay, so if we combine this formula, if we plug this quantity here, we have that, well, A time Vi is equal to V out plus A time V minus, which means that Vi is equal to V out over A plus V minus, which is this quantity here. So V out time R1 over R1 plus R2. Okay. So V input is equal to V out, which multiplies, well, let's have the same denominator here, so A plus R1 plus R2, which multiplies, well, the numerator is R1 plus R2 plus R1 times A. Okay, if I'm not mistaken, then we can rearrange this formula as V out over V input, which means A time R1 plus R2 over R1 plus R2 plus R1 times A. Yeah, we can manipulate this expression to highlight the original formula. So if with some algebraic operations, you can prove that this is equal to 1 plus R2 over R1 divided by 1 plus R1 plus R2 divided by R1 times A. So basically, this is achieved by dividing numerator and denominator times A, and then numerator and denominator by R1. Okay? So this is basically the original expression for the non-inverting configuration of the gain. and this is the degradation induced by the finite gain. So if A goes to infinity, this term is cancelled out and we fall back in the original expression. Okay, so indeed, non-idealities may affect the actual transfer function that we have in our C. Okay, let's take this into account. In the limit situation for the non-inverting configuration is the one sketched in this picture, which is called voltage follower topology or unitary gain buffer. In this configuration here, you see Vi again is connected to the positive input, but R2 is equal to 0, while R1 is equal to infinity. Okay, so basically this term here is null. Okay, so this can be very useful to decouple the effect of one node with respect to another one. So it's a unitary buffer in which we have a very high input impedance and a very low, typically, output impedance. This unitary buffer configuration can be used, for example, to generate an intermediate voltage when our power supply is provided by a battery. Okay, so we may want to generate, let's say, what can be considered the ground value between the top supply voltage and the bottom. Okay, so between V plus and V minus, we want an intermediate reference value, which will be our zero. Okay. So how can we do that? Well, we take the 9 volt voltage drop, then we apply a voltage divider with equally valued resistor, so that this intermediate voltage here will be, the voltage drop over here will be rigorously equal to 4.5 volts. Okay. So then we may add a capacitor to achieve a sort of stabilization effect. Okay, so low pass filtering effect, in order to avoid that irregularities in the voltage here are duplicated at this node. And then, well, you cannot connect this node directly to the circuit that you want to drive, because if this voltage divider is attached to a circuit with a given input resistance, so this is R1 and R1. Well, the partitioning between R1 and R1 is different with respect to the voltage division between R1 and R1 parallel Rin. Okay, if you had a resistance here in parallel, the voltage at this node will not be 4.0 volt anymore. Okay, because the voltage divider effect is different. You have Rin parallel to R1 divided by Rin parallel R1 plus R1 as voltage divider effect. Okay, so this should be multiplied by 9 volts. Okay, guys, I have to say you do not seem fully convinced. Are you still with me when explaining this thing, or not?
I think the capacitance is
I mean that this voltage here should be provided to other circuits. Okay, so Rin is the input resistance of the other system. Okay, so if you plug directly the signals, the circuit that you want to drive here at this point without this buffer, then you are affecting the voltage divider effects. Okay, while if you had this voltage buffer, since the input impedance here is very high, even if you plug the input impedance of the op-amp here, the parallel between a very high input impedance and R1 is R1. Okay, so you fall back in the desired R1 over twice R1 voltage divider effect. Okay? Let me further clarify. So whenever you have, so voltage divider is simply a circuit like this. R1 and R2. This is V out and this is, let's say, V in. If this is an open circuit, then the current which flows through R2 should be the same which flows through R1. The series of R1 and R2 is R1 plus R2. Okay, so the current which flows here will be V input divided by R1 plus R2. Okay, this current I1. The current here will be I2. And it is V out over R2. But if this node is connected to an high impedance circuit, no current can flow in this branch, and I1 is equal to I2. Therefore, you can equate this term to this one, and what you get is that V out is equal to V in time R2 over R1 plus R2. Okay? This is the voltage divider concept. So the problem is that if you add a finite resistance here, let's say R3, then you can check it, but the V out over V in relationship is totally different. In the orange case, V out will be V input time R2 parallel R3 divided by R2 parallel R3 plus R1. Okay, it's a completely different situation. Okay, and R2 parallel R3 will be smaller than the smallest value. So R1 in comparison will be more relevant in this expression. We don't want R3 Okay, so we place a voltage buffer here so that the input current in that branch is null. Okay, and we can fall back in this relationship. Okay, so this is the so-called split supply generator. Okay, so this is needed whenever we want an intermediate reference between a positive and negative supply voltage, starting from a battery. Okay, just one battery. Okay, of course, if you have two batteries, you can play with the intermediate level. Okay, so so far we have seen many different combinations of the inverting and non-inverting circuit. As I said, an important task is to match the dynamic range of the sensor with the A to D converter. Okay, so when we want to perform this matching, what we practice have to implement is a new circuit with an input-output characteristic which is linear and is conceived so that the smallest sensor output value and the largest sensor output value determine, together with the limit of the ADC range, 2 points, P1 and P2, and we must conceive the input-output relationship of the matching circuit so that it is a straight line passing through P1 and P2. Okay, so we have a linear dependency of the output with respect to the input. The slope is set by this value m, and B is used to express the shift between the origin. So when V in is 0, V out will be equal to B. Okay, so B is this quantity here. Okay, how can we implement this dynamic range matching function? Well, first of all, we have to take into account the fact that this M can be positive or negative, and the same applies to B. Okay, it could be less than 0 or more than 0. Okay, so we indeed have multiple combinations, actually 4 combinations. So M positive and B positive, M positive and B negative, and all the remaining combinations. Because the sensor output span can be in this relationship with the A to D input span, or we have a situation like this. So in this case, what we need is just a translation of the output with respect to the input of the ADC, while in this case we need also some gain because the sensor output span is smaller than the A to D converter span. This is a very typical situation. Or we may have a situation like this in which the ADC input span is larger than the sensor output span, but we need also some shift, okay, in the output. So these are indeed this multiple configuration we may be interested in. So all this relationship can be realized with different circuit topologies. So in case number one, when M is positive and B is positive, is provided by this configuration here. So how does it work in practice? So let's do some calculation. So the idea is that we have an input here. Then we have voltage divider effect, R1, R2, and here we have a reference voltage which is used to set the B coefficient. Then we have a non-inverting configuration. Feedback resistor is RF, and this resistor here is called RG. This is the output. So we want a relationship like this. V out is M times the input voltage plus a given quantity B. Okay? M and B are specific value which should be tuned to achieve the matching of the dynamic range of the sensor with the AGD converter. Well, how can we find B? Well, B is equal to the output when the input voltage is equal to 0. So we can null this input and find the output. When this quantity is null, so when we have a virtual ground here, this node V plus is equal to the partitioning of the reference voltage between R2 and R1. So V plus is R1 over R2 plus R1 times the reference voltage. V plus is the input of a non-inverting configuration. This is the non-inverting configuration. So we can use the formula of the non-inverting configuration to find the output. So the output will be V plus times 1 plus RF over RG. So basically, we can set B as V reference times R1 over R2 plus R1 times 1 plus RF over RG. Okay? How can we set the value of M? Well, M is V out over V input when B is equal to 0. Okay, when B is equal to 0, V out over V in is equal to M. How can we null B? Well, we can set V ref to 0. So B is equal to 0 when V ref is equal to 0. So now we can compute V out over V in. So when V ref is equal to 0, we have the ground here. We can cancel this guy. and compute V plus as V in divided between R1 and R2. So V plus in this new case will be, in this case, we have R2 over R1 plus R2 times V input. Then the relationship between V plus and V out is just the same. So V out is V plus times 1 plus RF over RG. And therefore, M is given by R2 over R1 plus R2 times 1 plus RF over RG. Okay? So you set M, then once you have set M, you can set B by controlling Vref. Okay? By doing so, you can achieve the sizing of the element of the circuit. Again, you can find here two capacitors. The role of this capacitor is to bypass high frequency noise, okay, in the circuit. So the possible non-instabilities of Vref are driven in this direction. Okay. Okay. In the next pictures. The next slide, you will find all the remaining combinations. Okay, so this is the case in which B is negative. Well, actually, what you can to better understand this combination, what you can observe is the fact that when you want to be positive, the reference voltage is somehow connected to the positive branch. And similarly, when you want an M positive, the input is somehow connected to the positive branch. In the following case, M is connected to the positive branch, so the input M should be positive, so the input is connected to the positive input of the op-amp, while B is negative, and therefore the reference voltage is somehow connected to the negative input of the op-amp. You can find these analogies in all the different configurations. So you see the in connected to the negative input here because we want a negative M. Okay, it is always the same mixing between the inverting and non-inverting configuration plus voltage dividing through the series of two resistors. This is the last combination when M and B are both negative. In all the slides, you can find also the full expression. The V out over V in relationship. Okay. Let's briefly discuss the offset. We will get back to this topic on Friday. By the way, Friday we will have just 1 hour time slot. Okay, so from 11:30 to 12:30. Okay. Because I'm involved in a project with a kickoff meeting on Friday. Okay, so the offset is indeed also very important non-ideality, which might affect a lot the behavior of our signal conditioning. The offset is a quantity which is very critical when we are using the op-amp to implement integrating function, because it is a constant input added to our system. So if we have to integrate this quantity, this means that sooner or later we will saturate the op-amp effect. So to model offset effect, the idea is to take the actual op-amp and model it as the combination of an offset-free op-amp characterized by the same gain of the actual op-amp, plus an additional unwanted voltage generator whose value is the offset value. Okay. The problem is that we can only measure this offset after the manufacturing of the op-amp. We cannot anticipate the value of the offset because the offset of a particular realization is given by statistical unpredictable effects. We have discussed the offset of CMOS op-amp, and as you see, this quantity can be quite relevant, from 5 millivolts up to 50 millivolts. Okay. If you trim somehow the op-amp to compensate for the offset, you can get lower values. But indeed, these values are quite high, especially if you compare this CMOS op-amp with respect to bipolar op-amps. So bipolar op-amps can achieve an offset value in the order of 10 to 25 microvolts. Okay, this is yet another reason why typically analog designer prefer to work with bipolar technologies. Okay, because the offset that you can achieve with a bipolar op-amp is much smaller with respect to the one you achieve with the CMOS, due to the fact that CMOS is affected by threshold variations, mismatching in the geometries, and this may cause this unwanted effect. These quite large quantities may generate an output even when in principle the input is null. So for example, here you see we have a non-inverting configuration in which the input voltage is null if we assume that the input is provided here. But actually, due to the presence of the offset, the output is not null. Okay, the output is the offset voltage time the gain of the non-inverting configuration. Offset is not the only critical effect of non-idealities due to the op-amp. Another critical effect, which in this case is more critical for bipolar than for MOSFETs, is the fact that we may have some biasing current flowing into the input terminals of our op-amp. Okay. This biasing current also means that the input impedance of this device is not infinite, and can be combined with offset effect to determine the global output response, which is far from zero despite having null inputs. Okay. I think that it's too late to discuss this formula. We will get back to this formula in the next class. Okay. Okay, thank you very much for your attention, and see you on Friday.